colleague is Dr. Karol Kudela from the Czech Republic. I obviously am from the United States by my accent. We have a very, very interesting session. We have 10 papers, not one of which is an invited chat talk, which I will give. And I'm going to ask all the audience, on behalf of myself and Dr. Kudela, to please stick to your 6 minutes. There'll be 2 minutes for questioning. And if you do that, the audience will be allowed to ask the questions, and so will we.
I would like to ask Professor Greenwald, first speaker, tema performance characteristics of mobile bearing total knee arthroplasty.
Well, again, ladies and gentlemen, I now address you as a speaker. Welcome to this session. And my challenge to you today is to present some remarks on contact stresses and kinematics in mobile bearing total knee arthroplasty, with also a reference to fixed plateaus. The continuing interest in the use of mobile bearing total knee arthroplasty is manifest by its clinical performance, which, like its fixed plateau counterparts, is seen to be dependent on what I'm going to refer to as an orthopedic triad, or a series of performance factors which are patient and surgically related, as well as design, material, and manufacturing choices. Mobile bearing knee designs were first introduced in the United States through FDA mandate, allowance is a better word, in 1984. And they more or less proceeded along without a lot of competition until about 1997. I'll go back one. When John Insel, who is certainly credited as one of the pioneers in total knee arthroplasty, made these remarks at a current concept CCJR meeting. Fundamentally, he finally got fired up about the prospect of mobile bearing knee replacement and was very, very interested in it and its avocation up until the time of his passing. So where are we with those? Well, to give you some idea of the global arthroplasty knee use, broken down between fixed bearing and mobile bearing, the white numbers indicating the number of fixed bearings implanted in around the world from 2008 to 2010, plus the number of mobile bearings. And one can see that the total number is just about 1 million, and mobile bearings dominate about 24% of this usage. Insight into their evolution is perhaps best gained by appreciating what happens at the extremes of fixed plateau knee design. The slide on your right is that of a virtually flat or totally non-geometrically constrained implant system, where indeed the only forces against movement are those produced by friction between the metal and the plastic. The advantage of these systems is that they move very easily. They transfer very low constraint forces to fixation interfaces. However, the bad news is that they generate very, very large contact stresses, which is, again, I'm sorry, I said right, it's on your left. As you move to the right, you gaze at a picture of a fixed plateau design that has a lot of conformity or congruity. To move that device through a range of motion requires effort to overcome the constraints imposed by geometry. And the bad news is that higher constraint forces are transferred to interfaces. However, the advantage lies in a complete distribution of contact stresses well below the slide on your left, which assists the durability of the ultra-high molecular weight polyethylene. So with that as background, mobile bearing knee designs, in fact, have these attributes. They increase proximal conformity between articulations. They allow the stresses to be distributed to low levels. And because of insert mobility, they reduce constraint forces that are transferred to fixation interfaces. These devices, in fact, may be characterized by telling you that a mobile bearing knee is characterized by a dual surface articulation between a polyethylene tibial insert and a metallic femoral and tibial metallic components. And it's because of this dual surface articulation in 1984 that the Food and Drug Administration required not just a clinical trial, but a laboratory evaluation. And we designed this simulator to satisfy that requirement. It's very, very simple. It mimics more or less the stance phase of walking gait between heel strike and toe off, about 20 to 30 degrees. We applied loads reported for compressive load as well as a lateral side load required by FDA, and characterized this first generation mobile bearing knee system, which was meniscal bearing, to calculate the volumetric polyethylene wear debris. And as one can see here, they varied. This was on the continuous saline drip, and we measured an amount of polyethylene after 5 million cycles, equivalent to that which has in fact been produced in fixed plateau designs of the day. These are what these early components look like. One can see here that after 5 million cycles, the geometry of the condyles are virtually unchanged. There are scratches and indentations, but when you turn the components over to look at their tracks, one will appreciate that, in fact, you can still see the cross-hatching of the you can still see the cross-hatching machine marks, and you can see the transfer of polyethylene to the track. And however, they remained in good stead, and this contributed to the clinical results with this device that led to the first approval of a device for mobility in the United States. This was rapidly followed by others, particularly the rotating platform, and these were eventually fell into disuse. They required a bit of technical ability, and in fact, they did require preservation of both cruciates. But however, there's a problem here. The problem is very simple. The construct of dual surface motion encourages distal sliding, seems intuitive of greater wear volumes. You're now moving articulations over two surfaces rather than one. And so, to any common sense approach, this would seem a more deleterious way to wear polyethylene. However, I would point out to you that the determinants of abrasive wear may be characterized by both sliding distance and surface stress distribution. The latter is brought home in a slide of work performed at MIT a number of years ago, and one sees a nonlinear relationship between increasing contact pressure and increasing wear volume. And this more or less defines one of the positiveness of this type of knee design. Well, to gain further insight, we've created a number of finite element models in the laboratory, attempting to measure the contact areas and surface contact stresses that exist across contemporary knee components. The one in your upper left is a popular device, the PFC Sigma fixed plateau. In the bottom is the LCS rotating platform. And what you see here are the contact stresses. The magnitude of these stresses is indicated by the scale on the bottom left here. And they start at 1 megapascal and go up to 26. One will appreciate that 1 megapascal is 145 pounds per square inch of contact pressure or stress. And when you get to about 20 megapascals, you are exceeding the yield point of the material, which means that the polyethylene becomes permanently deformed, and it is a first step in the durability of these components over time. The thing that is interesting that you should notice here is the differentiation between relatively low contact areas and fixed plateau designs and the benefit of increased contact area in the mobile bearing. You will also notice that the stress levels, lower to the left, higher to the right on the scale, are indicative here. Both of these designs are below the yield point of the material. If you turn them over, you realize that there are relatively low contact stresses as the loads are distributed across a much bigger area. Now, this is an important appreciation because it differentiates fixed and mobile bearing knee systems. So what I'd like to do now for the rest of these minutes is to focus on these areas. Contact stress and contact area is one, and let us look at three mobile bearing knee systems. One is the Oxford Unicompartmental, the LCS rotating platform, which I've showed you, the PFC Sigma rotating platform on the right. You will notice here that these contact areas are not insignificant, and the contact stresses which act across them are also relatively low. But of course the question is, what happens when you go through the full area of walking gait? The most interesting part is heel strike to toe off. Do these contact areas and contact stresses change? And I would suggest to you from our analysis that they do not. They remain reasonably constant, and the stress levels remain reasonably below the yield point of this polyethylene material. And this is an important feature to appreciate, because the dictate of what the contact area looks like and how it changes as you flex the knee is a function of the J curve of the femoral component. And it is important to realize that this is the most highly loaded cyclic area. In other words, repetitive loading as you walk, jump, or run that occurs during normal function. And this is a very severe environment, and you design into that environment. Okay. However, what happens when you get beyond walking gait? What happens when you begin to realize that 3/4 of the world population in Asia and in India, in the Middle East, squat as part of cultural, religious activities? This is not a typical position for an average American. And so the question becomes, how do these devices perform at higher flexion angles? To appreciate this, we continue our studies, and they're ongoing. We've looked at stair ascent, a 90-degree chair rise, and kneel rise at 135 degrees of flexion. And what do these tell us? These tell us this is the PFC Sigma rotating platform by example. One recognizes here that these are not insignificant stresses that are developed. You can see that even in the 60-degree flexion, you are above the yield point of the material. As you begin to rise further, particularly with posterior stabilized systems, you encounter the post. Those posts develop large stress levels, and those stress levels can, in fact, damage polyethylene, which is not the name of the game. You're trying to minimize damage over a long period of time. So these are, fortunately, these positions do not occur as the same frequency of walking gait, approximately a cycle a second. But it's not just a surface phenomenon that happens in polyethylene. It's what happens in the body of the polyethylene. What happens in its thickness. So you create a whole new system of stresses that have to be accommodated. Engineering-wise, these are referred to as von Mises stresses, but as far as we're concerned, they're stress volumes, and they tell you right away that these are not insignificant stresses. They rise, and at about 12 megapascals is a fatigue stress that will tell you that once you get above that, you really can damage components. So then the question here is, will these components survive will they manage their durability over long periods of time? And these remarks apply certainly to mobile bearings, but most certainly also to fixed bearings. Does this mean anything? Do you get damage? You certainly do. Knee retrieval, if you look at carefully, you'll realize that it's a function not just of abrasive wear, but the prima facie mechanism of damage occurs within the polyethylene known as fatigue delamination, where indeed you can see here in this retrieved failed fixed plateau design where the femoral component was internally rotated, that the kind of damage I've been referring to, in fact, is a clinical reality. Well, let's move now from stress levels to motion. How do these knees perform, both in fixed and mobile manners? So to appreciate that, we've done a lot of work in the laboratory characterizing total knee systems, both fixed as well as mobile. And what you're looking at here are the traces, the blue and red dots, the red being the medial and lateral compartment contact areas as you flex and extend to the limits of this design. And one you can see here is below about 103 degrees flexion, which is what this design allows. And you can see the contact areas shifting anteriorly and posteriorly. When you interpose a mobile plateau between these, the mobile plateau will tend to rotate externally, reducing the traverse of the medial compartment as it rotates slightly, but increasingly around the lateral component. And so this meets two qualifications: large contact areas, minimizing travel distance. Each knee system that we've evaluated, and they're into the dozens now, frankly has its own signature profile. The loops are the flexion extension pathways of these condyles as the contact areas traverse during flexion activity. So to give you an example, where does mobility occur in mobile bearings? As far as the Oxford is concerned, you have rotational mobility, you have unlimited AP mobility, and ML mobility. LCS, PFC, rotating platforms, you have rotational ability, but because of the stems, you do not gain the advantage of AP or ML. And fixed plateau, in the best of circumstances, are non-mobile, unless, of course, you have a poor locking mechanism, poor surface finish of the tibial component, and in time and turn, you begin to get many micro displacements. And there have been many components removed where you can actually see adhesive traces, which suggest rotational motion of these components. Well, material damage modes are important. I've stressed that, but let me stress it again. There are two. The primary surface damage mode of polyethylene inserts occurs beneath the surface of the device, and it's referred to as subsurface delamination. The secondary modality of damage in knees is abrasion. This is the direct contrast to the hip, where abrasion is the primary mechanism of material damage through wear. Okay, both of these can fracture. Let's look for just as an example. This is a fixed uni device. This is a mobile uni device. You can compare and contrast both fixed and mobile in terms of contact areas, contact stresses. We were unable to detect subsurface stresses down to 1 megapascal in the Oxford. Okay, precision manufacture is the sine qua non of mobile bearing knee production. Why bother developing a mobile bearing knee if you can't maximize the contact surfaces through functional activity? To answer that question, we've looked at, you must appreciate, as I just said, if you can achieve conformity through manufacture, you reduce surface and subsurface stress levels. This is a real example. In 1998, we were given this mobile bearing plateau to evaluate. We evaluated it, and of course the company wasn't very pleased with what we told them. We told them that they had really poor contact between the femur and tibia. It was performing more like a fixed plateau than a mobile plateau. I made the mistake of publishing this, and I'm forever in there. I'm in disgrace as far as they're concerned. But at the end of the day, we suggested to them that their method of femoral component finishing, which had been hand polishing, might better be served by computer-aided grinding. And when they did that, they kindly gave us one more component to evaluate, and of course they achieved what they wanted to achieve: large contact areas, low contact stresses. The last factor, and I leave you with this, are clinical factors. You'll remember at the beginning of my talk that I talked to you about patient and surgical variables as well as design manufacturing materials. I would suggest to you the clinical factors are the prima facie role that dictates often success or failure in a knee device. And I would point out to you the poor design, poor materials, poor patient choice, and poor surgery are the essential features of implant failure. I also will point out to you that knee arthroplasty, at the end of the day, is a soft tissue operation. I'll leave you with three really quick cases where these tenets were not appreciated. This is a rotating platform. After 5 weeks, the component completely spun out. The surgeon failed to appreciate the importance of balancing flexion and extension gaps, and as a result, he had laxity, and the component simply spun out, and that was a revision. This is an example of a revision. This is a meniscal bearing knee that I showed you at the beginning. The slide on your left indicates a lateral component meniscal bearing that had fractured and had been replaced with the bearing that you see on your left. And after 16 months, the same thing happened. You can, I call your attention to the radiographic metal markers. And when this component was retrieved and sent to us, it's almost guessable what happened. The femoral component was internally rotated. The surgeon failed to correct that at the time of the revision, and the component broke in exactly the same place that the index surgery where it broke. But the thing that's interesting, it follows the geometric contour exactly of the tibial plateau. So the last one that I will show you, then identifying the importance of tissue releases, is this is a bilateral patient after 3 years who returns for follow-up on walking on sticks. And I call your attention to the lateral AP position, anterior posterior position on the left of contact with the tibial component. On the right, you recognize a uncorrected deformity as well as medial subluxation of the femoral component relative to the tibia. On revision with trials, or the trial on your left suggests very much the reproducibility of that film. Posterior aspect of the femoral component in relationship to the tibial tray. And the surgeon had failed to fully resect the posterior cruciate ligament, and when that was done, it turned out to be a much more normal flexion extension range. So at the end of the day, what have I told you? I've highlighted the importance of patient factors, design material and manufacturing choices, and surgical variables are what I will call a performance triad, which are necessary to succeed, in my view, to achieve successful long-term knee arthroplasty results. So I leave you where I like to be, and it's real. I caught it. It even tasted as good as it looks. Okay, that's my talk. Thank you very much for your attention.
Thank you, Professor Greenwald, for a very interesting or nice paper, and we can start discussion. Any question from floor, please?
Well, if you're not going to ask me something, I'm going to ask you something. How many people, show of hands, use mobile bearing knee arthroplasty? Okay. I take it the rest of you use fixed plateau or you don't operate. Okay. I'm happy to answer any questions you may want to, well, I'll try to. You may ask me, sir. Mm-hmm. Sure. No. Well, like in most things, there, patient activity is a great factor in selecting what you use. Obviously, with senior citizens, we got a great track with all poly tibial components, fixed, cemented in place. With younger, more active patients, where indeed lifestyle is hopefully not climbing mountains, but or triathlons, they're more high-demand patients. So that's a very reasonable choice. In the United States, mobile bearings cost more than fixed plateau designs. They, in fact, are then. Economics is becoming much more important in the United States right now. We're struggling with trying to define what a healthcare system should be that provides care for everybody. So, I mean, your selection is, I wouldn't disagree with that at all. How many in this room do cementless? Has anybody experimented with that? You do. Do you differentiate there, sir, between? We have a whole new class of emerging. When cementless knee replacement was tried 20 years ago, its results were not very good. Techniques weren't evolved, nor were the material surfaces. Now there's a whole new class of porous materials that offer tremendous porosity, great fixation against native bone, trabecular bone, with reduced stiffness. And so I would suspect currently in the United States, 85% of all total knee arthroplasties are cemented. But that curve is being challenged as we move forward.
Other, please.
Sorry, just state your question. I think I know what you're asking. Say again. Yeah. Well, it's good you should ask that question. Industry is very busy in promoting the next best thing year after year, and they can charge more for the next best thing. There was a recent paper, in fact several, that came out of Korea, which compared same design, same product of high flexion to normal, and the normals did better. You have to recognize that as far as high flexion is concerned, oftentimes patient factors dictate what you end up with. In a highly obese patient, thigh to calf contact will dictate your flexion range. It has nothing to do with the design of the implant. The implant allows you to get there, high flexion designs, if in fact you can get there. They cost more. My suspicion is they will be around for more selected patients, but I don't think they're going to capture the day in terms of total knee arthroplasty design. I don't think everybody's going to get a high flexion knee, nor should they.
Do you combine mobile bearing with crucial retaining implant or posterior stabilized implant?
Okay. The first implant I showed you was meniscal bearing. That required the maintenance of a functional ACL as well as a PCL. You all know that in arthritic conditions, more likely than not, the ACL is either missing or severely compromised, totally incompetent. So they have two designs now. Designs will allow you to retain the posterior cruciate ligament or in fact sacrifice it. That becomes, that's almost a religious philosophy. It's like motherhood and apple pie. You either believe that sacrificing the posterior cruciate ligament and relying more on the device to give you flexion activity will suffice, or you want to retain the structure. There are reasonable results at both ends, and it becomes a question of surgeon choice and surgeon experience with the particular system. I will point out to you that no knee, fixed or mobile, that we have ever looked at, and we've looked at dozens and dozens in the laboratory in terms of how they move. Number one, they're all different. They never are exactly the same. And they are not the same as the normal knee. But they're a pretty good, reasonable approximation if your goal is relief of pain and return to reasonable functional activity. At that, I think we should stop and move on. And so, okay. So I am told that our second speaker has arrived. So I will ask Dr. Desai to come to the podium and present his remarks on long-term survivorship in the PFC primary.